Hi there and welcome again to the channel. In our previous 3 videos, we dealt with complex numbers. In our first video, we dealt with the introduction of a complex number, the definition of a complex number. In the next two videos, we dealt with the multiplication, the addition, the division of complex numbers. And in the third video, we dealt with the modulus, the argument, and the polar form of a complex number. We want to expand a little further on the analysis today by dealing with the exponential form of a complex number, exponential form. In other words, exponential, okay, exponential form. In other words, in a complex number z expressed in the form something multiplied by something to the power of something. You know what I'm talking about. But let's see how it works. Okay, so but now on the board I do have 3 functions, e to the power x, sine of x, and cos of x. And I have on the right of each function its expansion using the Maclaurin's series. So there is sine of x, there is of e to the power x, and there is your cos of x. All of them expanded using Maclaurin's series. Let's play a little game here. We have e to the power x, and that's the expansion there. We want to replace x by I multiplied by theta. Remember, I is our imaginary number. So we want to replace that with x, and wherever we have an x, we're going to put in I theta. So let's do that and see what happens. So we have here, this will look like, let me see if I can clear this here. It will be standing in the way. So we have here e to the power I theta will be equal to, there's a 1 there, and then an x, which is I theta, then an x squared, which is I theta squared, plus I theta squared divided by 2 factorial, followed by I theta cubed 3 factorial, followed by I theta to the power 4 over 4 factorial, followed by I theta to the power 5 divided by 5 factorial. Now we know from previous videos that I squared is equal to minus 1. So here we will have a minus 1 multiplied by theta. When I is cubed, we have, let's just do a little calculation here. We said I squared is equal to minus 1. I cubed is equal to I squared multiplied by I, which is equal to, this is minus 1, so that gives you minus I. I to the power 4 will be I squared, which is minus 1, times I squared, which is another minus 1, so that becomes a positive 1. So with that in mind, let us deal with these terms here. So we have here, this is equal to our 1 here, plus our I theta, of course, nothing happens. Then here we have an I squared, which will give us a minus theta squared over 2 factorial, because the I squared gives us a minus 1. Here we have an I squared times an I, which is a minus 1 times I. So that gives us a minus I theta cubed over 3 factorial. What about here? We have an I squared times an I squared, which is minus 1 times minus 1, which is a plus. So here we get a plus theta to the power 4 over 4 factorial. Here we have an I squared times an I squared, which is minus 1 times minus 1, which is a plus 1, times an I when they are risen to the power 5. So it becomes a plus I theta to the power 5 over 5. Okay, So now when you look at this, there are terms which have an I in them, in other words, imaginary terms, and there are terms which are free of I. Let's just quickly mark them in blue if we can, or red, so that we can quickly distinguish them. Here, this one, there is no I. There is no I here. There is no I here. Right. So the other ones have an I. 1, 2, 3. So let's group them together. The ones with an I and the ones without an I. So the ones with an I will be 1 minus, I hope I am not blocking your view, theta squared over 2 factorial. The next one there will be plus theta to the power 4 over 4 factorial. And this, of course, would extend. If we were to go on and on and on, we would be able to identify this, and they would extend to infinity. So I've put them in brackets there with the 3 little dots to indicate that this is something that goes on and on and on. Okay, now let's collect the terms with an I. Let's just put our I outside that bracket. So we will have here, the first one is just theta, because we remember it's multiplied by I. The next one will be minus theta cubed over 3 factorial. The next one will be this one, which is plus theta to the power 5 over 5 factorial. And it goes on, so we put our bracket there. Now, we have 2 groups of terms. We have grouped the ones that are free of I and the ones that do contain an I. Now, when you try to compare them with what we have for sine of x and cos of x, you can see that the first group here, the ones that are free of I, they are really the expansion of cos of x, because there's a 1 there, x squared there, x to the power 4 there, and so forth. We could have put an x to the power 6 if we wanted, and so forth and so on. So this really here boils down to the expansion of cos of x. So we can write this as just our cos of x. I'm looking for I'm just trying to look for something red. Okay, there it is. So this really is cosine of x. Remember, cosine of x is this when it's expanded. So this represents cosine of x. What about the next group there? You can see now that there's an x there, which has been replaced by a theta, x cubed, that one there, and so forth, up to infinity. So this one here is really the expansion of sine of x. So this is sine of x. Right. So what does it mean? It means that e to the power I theta, remember we had to replace x by theta. So if we replace x by theta, we end up with this, which is actually cosine of theta multiplied plus I multiplied by sine of x, sorry, sine of theta, sorry, what am I doing? I should be writing theta there. I'm looking for my, yes, okay, sorry about that. This is now theta, right? Cos of theta, okay? Same applies here, it's cos of theta. Let me just repeat this slowly. What we did was, we had e to the power x. We replaced x by I theta, and we expanded it in the normal way, just as it is expanded there. Then we identified terms. After simplifying the powers of I, we found that certain terms do not have I with them. And these terms, we grouped them together, and here they are. Then we found that there are some terms which are left with an I, and we grouped them together. Of course, all of them are multiplied by I, so here they are inside this bracket here. Now, when you compare this first bracket here with this, it's exactly the same thing. So this must be the expansion of cos of theta. And this similarly must be the expansion of sine of theta. So what it means is that if you raise e to the power I theta, this is what you get. So let's write it down. So e to the power I theta is equal to cosine of theta plus I, let me write the I to emphasize something here, plus I multiplied by sine of theta. So that's our result now. Okay? E raised to the power I theta is cosine of theta plus I sine of theta. What has this got to do with anything? Okay, so I'm going to clear the top of the board because we just want to continue a little bit further with this to get to our final destination, which is to express a complex number in exponential form. So let's get rid of all this here. Okay, so what we have now is, first of all, we found that e raised to the power I theta is equal to cosine of theta plus I sine of theta. But we know that a complex number, from our previous video, a complex number z can be expressed in polar form as r brackets cosine of theta plus I sine of theta. But what is this inside the bracket? Of course, this would be the modulus of the complex number, and this will be the argument. But everything inside the bracket is actually that. So we can write z as r e to the power I theta, where I is our imaginary number, theta is the argument of the complex number, r is the modulus. This is the exponential form of the complex number. Remember, this is the polar form, where again that's your argument, that's your modulus. You change this, it can give you that, where this again represents the same quantities. Now, let's take just one example before we go. I keep losing my duster. Okay, so supposing we are given a complex number. Let's say we are given z is equal to 1 plus I. Okay, that's our complex number. All right, so we wanted to change this. This is the rectangular form of the complex number, or the standard form. It's in rectangular form. You want to go to this first and go to that. So what is the modulus of z? We know that z is equal to the square root of 1 plus 1 squared. 1 squared plus 1 squared, which is equal to the root of 2. That's the modulus of z. What is the argument of z? We know that arg z, I think my pens are giving up here. Arg z is equal to arctan 1 over 1, which is equal to what? Which is equal to pi radians, 45 degrees. The angle whose tangent is 1 is 45 degrees. So therefore, in the polar form, z is equal to root of 2 brackets cosine of pi plus I sine of pi over 4. Sorry, I don't know why I'm writing pi. It's pi over 4. Pi over 4, which is 45 degrees. Okay, that is z in polar form. What about z in exponential form? Again, we know our modulus is root of 2 our argument is pi over 4. So z can also be written as root of 2 e to the power I pi over 4. This is the exponential form of z. This is the polar form of z. This is the rectangular form of z. So let's write it here. Exponential form. This one would be your polar form. And this, of course, here is your rectangular form or standard form. Let's call it rectangular form of the, is that the name? Sorry. Rectangular form. Okay. Rectangular form of the complex number, polar form of the complex number, exponential form of z. Okay, so that's it. What is left for us, as is usually the case, because our program is to solve past examination questions. Our next video will be dedicated to solving a past examination question. I hope I'll get a nice and juicy one. Till we see you next time. Bye-bye.